have one issue. I didn't record. I didn't start the record, but it's okay. Maybe okay. I'm very ashamed about the fact. I realized that just now. Okay, but we continue the lecture. I explained the standard products in square metric space, and after that I will define other standard product like the polynomial space. Pn is the polynomial space with of degree less than or equal to n. That means the vector P is a0 plus a1x plus a2x squared to anxn, and I'll give another vector b q b1 b0 plus b1x plus b2x squared to bn x to the n. In this case, I will define the standard product. Product which is called standard product. P product Q is equal to a0 b0 a1 b1 an bn. I have typo in my lecture notes, which is called the standard product. And actually it is very similar to dot product. And what? X is just a polynomial. When you consider the space of polynomial, it is needed non-determinants, indeterminants, polynomial with indeterminants x. So it is just polynomial. So when we consider the products, we need to get the real value, and so the polynomial is defined by the entries, and actually it has one term corresponding to the R to the n plus 1 vector space with a0, a1 to an in the vector space R to the n plus 1. So we will give standard product with the standard product in this space. The polynomial Q will correspond b0, b1 to bn, and its standard product was here. It was that product, and it is same to the space of polynomial space of degree less than equal to n. And also we can define the standard inner product in continuous function vector space, that f b or f x and g b or gx in continuous function which is defined on the interval, closed interval a to b. Here a is less than or equal to b. I will say strictly less than b. Then the inner product fx is the integral from a to b fx gx dx. Actually, it also will be satisfied with the inner product statements because it has symmetricity, and the integral has the linearity if you calculate k f1x plus f2x multiplying gx integral, then it will have distribute rule and additive rule, so it will give k integral f1x gx dx plus integral f2x gx dx, and with each integral has f1 inner product g, f2 inner product g. So if you define like this, and I also check one more, f inner product f is a b f square dx, and I will write here. F square is it was defined it under real value. If f is a real function, then x squared is real number. So it is positive number, and so it will have positive value. So it is also inner product, and actually the equal if and only if fx equal to 0 for all x in the interval. So it, which is called it the standard inner product. I think that's the standard inner product because it depends on A and B. And I think we have limited time, so are you okay to do more, or I will do until this theorem. So let's UVW is in the vector space, in a product vector space, and K is a scalar. Then I'll give some properties. If you inner product with 0, then the value should be 0, because you consider a linearity. It is same to 0 u v, and the linearity will give 0 u v, and multiplying 0 is always 0. You can consider like that. And I explained already we give the axiom for the first vector of inner product, but the symmetry give the linearity to the second vector. So it is saying to UV addition, UV edit, UW, and also the scaling, the minus case also same, and the scaling case is also same. K inner product UV is equal to U inner product KV. Also, it is same to the property U minus VW is also equal to UW VW. So finally, I will calculate an inner product U minus 2V 3U plus 4V. If you calculate it, then by using this property or the definition of inner products, it can be written U 3U will give 3U inner product U, and U 4V plus minus 2V 3U. So 4 minus 6 UV. It has symmetry properties, so I will write as the same component, same term. And finally, minus 2V product 4V is minus 8V in a product V. So it is same to the norm square of U, because we defined it square root U in a product U as the norm. So by squaring, we can get that back. 3U square minus 2UV minus 8V square. We can calculate it as this form. And actually, by using this form, next class we will reconstruct it by the norm, from the norm to the inner product. And I also explain how to describe arc by giving from the given inner product.